Welcome to Lesson 17, How Derivatives Affect the Shape of a Graph. So what we're basically going to do in this lesson is just build on the concepts that we've developed in previous lessons and apply those to how derivatives directly tell you information about graphs. Instead of starting with a graph of a function and then creating a graph of its derivative, we're going to use the derivative to tell us information about the graph of a given equation. So what I'd like you to do to start is we've already talked about, intuitively what increasing and decreasing for a function mean and how that relates to the derivative. But I want you to take a minute and just pause the video, read these definitions for increasing and decreasing and constant so that you're aware of what the mathematical definition is for each one, and then fill in the bottom here for the increasing, decreasing, and constant functions. What kind of tangent lines do they have? Are they uphill, downhill? And what does that mean about their slopes? Okay, so just to solidify what we've already talked about, if you're looking at an increasing function and you draw in some tangent lines, these aren't my best work, but we'll deal with it. All of these are uphill lines from left to right, which means they have positive slopes. So that means that the derivative, which is equal to the slope of the tangent line, will always be positive wherever a function is increasing. Same idea, just in reverse for decreasing functions. Now our tangent lines are downhill. So they'll have negative slopes, which means the derivative will be negative. We've already talked about this, but we're really just laying it out in picture form here. And then a constant function, really a tangent line, is just the same as the function itself. They have zero slope, so the derivative would be zero at a point where the function is constant. Okay, so what that basically does is allow us to translate into a way to test if we have an equation and we look at its derivative, we can tell the following. If the derivative is positive on some interval, then that means the original function is increasing on that interval. And if the derivative is less than zero, negative, on some interval, then the original function is decreasing. And if we did have some interval where the function was constant over an interval, where the derivative was zero on an interval, then what can we say? We can say that f is constant on that interval. Okay, so basically what this allows us to do is take a function such as this, which I don't know what the graph of this looks like, but I can find the intervals of decrease and increase by taking a derivative and making a sign chart, figuring out where is the derivative positive, where is it negative. So let's give that a try. We're going to take the derivative of this function. It's a polynomial, so that's not terribly painful. And then in order to make a sign chart, the first thing that you need to do, so I'm just going to find intervals of increase and decrease, is basically telling us to make a sign chart for f prime of x. Okay. But in order to make a sign chart, the first thing you have to do is figure out when it's equal to zero and when it's undefined, but in this case, it's defined everywhere. So that looks like in this case, I'm going to start by trying to factor out the GCF, which is a12x, and then I can factor what's left inside. So it looks like I have three zeros, x equals 0, x equals 2, and x equals -1. So if I throw those onto a number line, -1, 0, and 2. Remember, when you make a sign chart, I put the zeros up here, up above, stands for what the function is doing, the f of x is, and these down below are the x values. And I always like to label my sign charts like what function it is, because we end up making more than one sign chart in a problem sometimes. So we need to know which one is which. Now, the next thing you're going to do is pick test numbers from each one of these intervals, plug them into the derivative. I suggest you plug them into the factored form because all you need to know is whether the function itself is positive or negative at that point. So if I plug in something less than -1, like -5, this will be negative, negative, and negative. So negative times a negative times a negative is negative. So I put a negative over that interval to indicate that the derivative is negative there. So then I'm going to plug in something between -1 and 0. So -1/2. That's going to be a negative, still a negative, and now a positive. So negative times a positive is positive. Keep going. Plug in something between 0 and 2, like a 1, positive, negative, positive. And finally, something bigger than 2, like a 5, positive, positive, positive. And I like to add in, once I've done these intervals and I'm using them to tell when is a function increasing or decreasing, I just put in the extra visual underneath. So where it's negative, that means that my function would be decreasing. And where it's positive, that means that my function will be increasing. So I kind of get a little visual down below. I can see where increase and decrease is happening, but then I will report them as intervals for my answer. So it appears to be increasing on -1 to 0 and 2 to infinity, and decreasing on -infinity to -1 and 0 to 2. So that would be my final response. And you can always double check by taking a peek at its graph. Again, I don't know what this graph looks like off the top of my head, but I did throw it into the graphing calculator, and I can see that this function is decreasing pretty much. I mean, it's going to go on forever. So it's decreasing up until, looks like that's a -1, since it's a -1. And then it increases to 0. Then it decreases. Oh, where does it stop decreasing? Let's scroll down. Decreases to here, which looks like, yep, that's at 2. And then it increases forever. Okay, so if we go back to our answer, you can see that that corresponds to what we found by using the derivative. So what I'd like you to do is, again, just pause your video and do the same process, but now you're going to do it for this second function, g of x, which is 1 over x squared. Okay, and keep in mind that when you go to make your sign chart, those places where you're going to put these markers of endpoints of intervals will be either when the function or the derivative is equal to 0 or when it's undefined. Both of those make those little markers. Okay, so go ahead and pause. Okay, let's see what we got. So I rewrote this function as x to the -2, took the derivative and wrote it as -2 over x to the 3rd. Now this is never going to equal 0 because the numerator is never 0, but it definitely does not exist when x equals 0, the denominator. So when I went to draw my g prime sign chart, I put this 0 where it doesn't exist at the bottom, but I put a u over it instead of a 0 because this is not where g prime equals 0. It's where g prime is undefined. I plugged in something less and greater and got positive here and negative there. It's pretty straightforward to plug those in. So it looks like it's increasing on the interval from -infinity to 0 and decreasing on the interval from 0 to infinity. And in fact, you should know what this graph looks like. Well, that is, again, some of my finest work. It's roughly this. And what's happening? It's increasing and then it's decreasing, exactly as our sign chart predicted. So this is a pretty powerful way to learn from an equation what's happening in terms of increase and decrease in a graph. So we're going to build on that just a little bit for the next piece, because beyond just increase and decrease, we want to figure out where these maxes and mins could possibly be, and particularly local maxes and mins or relative extrema. So these intervals of increase and decrease are the last piece of the picture that we need in order to finish figuring out where our relative extrema are. So we already talked about the fact that we know that relative extrema can only occur at critical numbers, but that not every critical number is a max or a min. So just again, this is a little bit of review, but I think it's really helpful. Well, that's close enough. Well, we'll say that that results in a function. It's really helpful to review these ideas because these are important. So I have a max somewhere up here, which is a critical number. The derivative is 0. I missed my tangent line, but you know what I mean. We've got a min down here. It's also a critical number because the derivative would be 0. And I have a relative max here, which is also a critical number because the derivative would be undefined at that cusp. So here is a place where all of my local extrema are occurring at critical numbers. But I could take a function like tan x or something similar. And I do have a critical number in here somewhere where the derivative is equal to 0, but there is no local extrema at that particular critical number. So if it is an extrema, it's happening at a critical number, but not every critical number results in an extrema. Remember, we've talked about this already. So what's the difference? What do you see happening in the first picture that you don't see happening in the second picture? Maybe trace the function. So the function, in order to achieve this max, is going up, and then what's happening? It's going down. What's happening on this minimum? It's going down, and then it's going up, and then going down. What's happening on the other side? It's going up, and then it's still going up. So it changes from increase to decrease or decrease to increase at that critical number, as opposed to not changing, staying from increase to increase, or it could have been decrease to decrease. That's the final piece that we need. So a max or a min occurs when the function switches from increase to decrease, or vice versa, could be decrease to increase, right, at the critical number. And if we're looking at the derivative, what does that mean is happening at the derivative? If the function goes from increase to decrease, then the derivative goes from positive to negative, or negative to positive. So what that's telling us is that f prime of x changes sign at the critical number. And that is the piece that we need to say there is a relative extrema at that critical number. Okay. So the first derivative test is basically putting all of these things together. It's saying start with a critical number of a function, so we'll call that c. If the derivative goes from positive to negative, it should say at c, not and c. Sorry about that. At, these should probably all be at. If it goes from positive to negative, the derivative, that would be increase to decrease so it's going to be a local max. If the derivative changes from negative to positive, decrease to increase, then it's a local min. And if it has the same sign on both sides, then there is no relative extrema there. So the first derivative test is the piece that will put all of these things together. So we're going to just follow up on the last example, one of the last examples we did. Find the relative extrema for each of the following functions. So from the last example, this was the one we just did. So we're just going to copy and our sign chart here for f prime. You can look back, we had critical numbers at -1, at 0, and at 2. And the function switched from negative to positive to negative to positive. And again, when I draw these arrows in, it's almost like you can see the maxes and mins happening, right? You can see that min here and that max here and that min here. Okay, so decrease to increase, that's a min. Increase to decrease, that's a max, etc. So we're going to have a local or relative minimum. And oh, the other thing to keep in mind, is that extrema are which values? The x or the y? Yes, the maxes and mins are the y values. So what I need to do is I need to take this -1 and plug it into this function. And when you do that, you're going to get 0. So I have a local min of 0 at x equals -1. I have a local max of, let's see, I need to plug 0 in, which is pretty easy to do. And then I have one more local min at x equals 2. And if you plug 2 in, I got -27. So I have 2 local mins, 1 local max, just from plugging in those values after I created the sign chart, which we did in the last example. Okay. So what I'd like you to do one more time, pause the video and do the same process. We haven't done the sign chart for this one yet. So you're going to need to take the derivative, create the sign chart, and then tell me whether there's maxes or mins. So go ahead and pause and give that a try. Okay, so let's see what we got. I took my derivative using the chain rule. I set it equal to 0. So 6x will give me a root of 0, and x squared minus 4 will give me 2 roots, plus and minus 2. So I put those all on my sign chart. They're all zeros. And then I plugged in some test points. One thing that's really important, could really actually make your process go faster, is you see how this x squared minus 4 is squared? So everything that comes out of this is going to be positive. So it really only matters what happens at 6x. So negatives are going to make it negative and positives are going to make it positive. Don't fall into the trap of thinking that these things are always going to alternate positive, negative, positive, negative. Here's a great example. They don't. So I do have a decrease, decrease. So there is no local extrema at -2, and I have an increase, increase. So there's no extrema at +2. And do you see how my arrows kind of show me that? But I do have a min. So if I plug in 0, I have a local min of -64 at x equals 0. And that is all that we have. And actually, if you just wanted to take a look at what that looks like, go back to my graphing calculator here, and I've plugged that one in, and you can see, I can kind of zoom in, that it does flatten out at both -2 and 2. So it does have a 0, a horizontal tangent there, but no max or min. And it isn't until, I mean, I'd have to scroll way down to -64 to see that actual min.